consider this system right here, okay? This is a homogeneous linear system, and it's got constant coefficients, see? And if we wanted to write that in matrix form, here it is, okay? Or more generally, it looks like this, okay? Now, what we want to do here is proceed how we did previously when we were solving homogeneous linear differential equations with constant coefficients, and we assume a particular type of solution. In fact, we're going to assume that the solution is this vector here, and this is a vector. Maybe I should put an arrow above it, but I've got an uppercase K, e to the lambda t. We're going to assume that this is the general structure of the solution. It's got a vector in front, and then e to the lambda t. Now this k, like I say, it's a vector, and it's got these components, k1 and k2 in it. Okay. So, if we do that, let's see what happens. When I differentiate this, I get this. Okay. So just differentiating with respect to t. So now, look what we have. We have that the derivative, x prime, right here, this thing, x prime is this, and then on the other side we have a, and then the solution right here. Okay? So let me maybe highlight that. We've got this, which is this right here, and then we've got in blue this. Okay. Now, I want to just do a little work here. Notice that I can divide out this e to the lambda t. Let's just divide that out. And I get this. I get this last part right here. Okay? Now, we could then subtract the lambda k from both sides, and we get this equaling 0. And then I'm going to factor out the k. Okay? I'll just pull this k out. And now I've got this on the inside. Now, notice I put the I in there because lambda is just a number. If I didn't put the I in there, it would be this matrix minus a number. Well, it needs to be, the matrix A needs to be, you know, if it's a 2 by 2, I need to subtract off a 2 by 2 matrix. I don't just subtract off a number. So what I do is I put the identity matrix in. So I factored out the K, and now I've got this in the inside. Now, what we're trying to do is we're trying to find this thing right here, this K. That's what we're trying to do, see? Because we're saying, okay, this vector is part of our solution. Now, we're going to assume that that K is not 0. Because if it's 0, then heck, that's just a trivial solution. We're just saying, well, K1 and K2 are 0. Okay, so the solution is 0, the 0 matrix. Well, we don't want to do that. We want to find a different solution where K is not equal to 0. Now, recall back when you were, I don't know if you remember this, but whenever you're solving a system of equations like this, and you've got, these are all matrices, okay? Every one of these are matrices. And you want to solve this for capital X here. What you do is you multiply both sides by B inverse. Okay? So I'm going to multiply. Now notice I left off something here. I've got B, and here I've got B inverse. Okay? So I multiply both sides by the inverse of B. And then over here, this B inverse B becomes just the identity matrix. and I've got x equals b inverse c. And there you have it. You have solved for x. Now, suppose that for this a minus lambda I, suppose that an inverse exists. Then you would say that k is equal to a minus lambda I inverse times the zero matrix, or the zero vector. Okay? In other words, you're solving this. That would mean that k is equal to the zero vector, but we already said, yeah, we don't want that to happen. So what we have to do is we have to ensure that this a minus lambda I, we have to ensure that that inverse does not exist. And the way we ensure that is by finding values that will make this determinant 0. Because if the determinant's 0, the inverse doesn't exist. And that's a necessary step that we have to do. So, let's look at this particular problem here. We've got 4, -3, 6, and -7. We're putting this in matrix form. That's our matrix A. So now look, we're gonna do the determinant of a minus lambda I. Well, that's this right here. See? A, that matrix minus the identity matrix times lambda, and what we end up getting is on this main diagonal, we get those values minus lambda. See? Because -7 minus lambda and 4 minus lambda. Okay. Now, so let's find that determinant. I multiply these together minus multiplying these together, and I get this. Okay, working that out, clearing parentheses, I end up with this thing right here, which I can factor this way. And solving that equation, I get lambda equals -5 or lambda equals 2. These are called eigenvalues. So we have eigenvalues there. Now we use those eigenvalues to find eigenvectors. And the eigenvectors, that's the k that we're looking for. The k, this right here. We're looking for eigenvectors, and k is an eigenvector. Okay? So here's what we have now. So let's set out now to find these eigenvectors. So I'm going to let lambda equal -5 and plug back into A, or this thing right here. Okay? So I'm going to plug back in 4 minus -5. -7 minus -5. And I'm going to multiply that by K1, K2. And I'm going to use that to find the K1 and the K2. That's the big K. That's the eigenvector. Okay? So what we're doing is we're going back to this. We're assuming the solution looks like this. Okay? So I'm trying to find this thing right here. Okay? Okay? Now, when I go through here, I get this system of equations right here. If I just multiply, I get this system of equations. Now, this system of equations is a dependent system. You can't go through here and use the elimination method or the substitution method or any of that and expect to get a solution for K1 and K2. Because remember where this came from. We deliberately set up a dependent system. See? I mean, look, I did this, and I got lambdas, and now I'm plugging those back in. Of course, that's not going to have a unique solution. So what we do is we set out to find an eigenvector by this method. I'll take K2 and solve it in terms of K1, like this right here. And you could go a different approach. You could solve K1 in terms of K2, but now I get this relationship here. Now I can just pick any value I want for K1. And for simplicity's sake, only for simplicity's sake, I'll just let K1 be 1. Now, if K1 is 1, then K2 is 3, and I get this, my first eigenvector. K1 is 1, and K2 is 3. So now we have our solution, one solution. K1 is equal to 1, 3, e to the negative 5t. And notice where I get the negative 5, right there. Now, I do this same process for the eigenvalue of 2. So I plug that back in. I get a dependent system here, which I can't solve. But I can find a particular solution. I can find one eigenvector. Okay? I'll just pick one. So what I do is I say, okay, well, K1 is equal to 3 halves. Okay? If K1 is equal to 3 halves, then what about if I choose K2 to be 2? Okay? If I choose K2 to be 2, and I put that in here, then K1 is 3 halves times 2, which is 3. So I get this eigenvector. Now, if I get that eigenvector, I have another solution right here. So now I've got two solutions. I've got x1, x2. Both of these are vectors. Okay? And I get my general solution this way. See? C1, x1 plus C2, x2. And there you have it. Now, sometimes you'll have repeated roots. Okay, so you'll have repeated eigenvalues, I mean. So, for example, in this problem right here, we go through this process that we just went through, and we get this situation. Or actually, we get this situation right here. I skipped ahead a little bit. So I get this. Now, this means that lambda equals 5. Now, if we then use that, plug back in, we get this situation, okay? I go through the same process as I did earlier. I said, okay, well, K2 is equal to negative K1. And I'll say, well, K1 is equal to 1. Then K2 is negative 2, and I get this. So I get a solution. Here's a solution. 1, negative 2. Now, we have to find the second solution. So we're going to proceed in a similar fashion that we did when we were first talking about repeated roots in the when we talked about homogeneous differential equations with constant coefficients. So we're going to take that eigenvector, okay, and we're going to take this solution, but we're going to put a t with it. So it's going to be k t e to the 5t, right, like this. But we're going to add another term. We're going to add another vector, this p, which you can think of it this way, e to the lambda t. So we're using the same lambda as we did earlier. In this case, it's going to be 5. So this is the general form that we're going to take. Now, to see why this works, we just put this back in to the differential equation. In other words, we've got this right here. See? So we're going to plug back into this. So I put in the derivative. Okay? So I'm putting in the derivative right here. I'm just taking the derivative of this and putting it in right here. Okay? And then on the other side, I have a times that solution. So here's a times this. Okay? Now, I do a little algebra, a little bit of rearranging, bring everything on one side of the equation, and so that I get a 0 on one side. There's the 0 over here. And I do some regrouping. I take all the t e to the lambda t's, group those together, and I get this. Group all the e to the lambda t's, and I get this when I factor out. And by the way, this 0 over here is of course, it's a vector. Okay. Now, when I do that, here's what has to happen. All of this stuff has to be 0. Okay. For all values of t. So for all values of t, this has to be 0. That means that this right here, this has to be 0. Okay? And this also has to be 0. Both of those have to be 0 for all values of t. Now, for this top one right here, we get this, and that doesn't give us anything new. We already had this equation that we looked at earlier, and we found the eigenvector k. So we already have the solution that comes from exploring this. We get the eigenvector k. What we need to look at is this to get the second solution. Okay, so that's what we're going to do. We're going to look at that thing. Now I noticed in my notes here that I put k's there. These should be p's. Okay, p1, p2. Yeah, there we go. So now I'm going to solve this. I've got p1, p2 equals, now, so I'm just solving this equation right here. Okay. And I get this right here. And I say, okay, p2 equals 1 minus 2p1. See? Okay, so then I say, well, let p1 be 0. Nothing wrong with that. Then that means that p2 equals 1. So now we have our, now we have what we were looking for. And this is, by the way, this is p here. Okay. So now we have the p. So look at the solution. We have our general solution. We have our first one. This is what we got earlier. Okay, times a constant. Plus a constant times the second solution. The second solution is this, see, which is this form right here. Okay, now next time what we're going to look at is complex eigenvalues. So what do we do if we have complex eigenvalues? How do we find the eigenvectors? So that's what we'll do next time.